photon doesn't disappear entirely, but it passes some of its energy off into the electron, both.
It will, yeah, it will typically put some energy into the electrons, but that's not what we're concentrating on here. Yeah, so if I've got, happen to have a stationary electron and a photon scatters off of it, by momentum and energy conservation, the electron will have to pick up some momentum and energy as a result of the scatter. So, yes, and that will change the wavelength of the photon because it's given some of its energy to the electron that it's scattered off of. Yep.
And for absorption, then it gives off all of its energy.
Yeah, for absorption, it gives off all of its energy instead of just some of its energy. Yep. Okay, so this is the equation we're starting at. Notice that another way to put it is that di lambda ds, the derivative of I lambda with respect to distance along the beam, is minus kappa lambda rho times I lambda. So in other words, this implicitly is a differential equation we wrote for I lambda as a function of s. And you have a convenient thing that you can push to keep the coffee from coming out, and then you forget to do that. You're like, where's the coffee? But another way to do this, another way to write an equation like that is to separate it. Have you taken differential equations yet? Yeah, so a standard technique is, this is a separable differential equation. So I can say, yeah, di lambda over I lambda is minus kappa lambda rho ds, and then I integrate both sides.
Kappa lambda is
it's the opacity. It's the opacity, and it depends on wavelength. But we're assuming that it doesn't depend on anything but wavelength.
Okay.
So in other words, it's a characteristic of the gas, the atoms that are in it. So
it's an intrinsic property.
It's an intrinsic property, exactly. It's an intrinsic property of the mix of atoms and other particles that are in the gas.
Okay. That's why we then take it with the.
Yeah, it only depends on, it's a constant for any given lambda. Let's put it that way.
Okay.
It's a constant for any given lambda. And we're trying to find I lambda specifically. In other words, the amount of absorption depends on wavelength. But for a given wavelength, kappa lambda is a constant intrinsic to the material. And so we can do that separation. That kappa lambda is just a number if you keep the wavelength constant. Okay. If we were trying to do this over wavelength, then yeah, kappa lambda would have to be folded over to the other side. So, 2, 4, 6, 8, it's now time to integrate for a light beam with I lambda equals some I lambda naught at s equals 0. Yeah, we're gonna find, we get an exponential type thing. So we'll say I lambda equals I lambda, I sub lambda comma naught at s equals 0. We have that, well, you integrate both sides and the limits have to correspond to one another. So the integral from I lambda naught to I lambda of di lambda over I lambda will be equal to minus the integral because of the minus sign there, and s equals 0 corresponds to I lambda naught, and then s is I lambda wherever we are, and then I'm going to be a good mathematical citizen, which physicists often are not, and I'm not going to call the integration variable by the same name as the upper limit. So I'll integrate with respect to ds prime. physicists are very bad about not obeying that. Just say, well, it's understood, of course, right?
Yeah.
But no, I like to be a good mathematical citizen. Now, rho in general depends on position within the beam. It might be traveling through an atmosphere where the density is decreasing with height, for example.
Okay.
So I don't get to take that out of the integral unless I say that rho is constant, but I'm not going to assume that here. So here we're going to get that log I lambda over I lambda naught, because this will be log I lambda minus log I lambda naught, and then the difference of the log is the log of the ratio, is equal to, and then we're not going to be able to do any better than say whatever this integral is,
Because we don't know.
because rho depends on x.
And
Yeah.
we don't really
So
know.
this will be whatever this integral is, right? You just have to leave it unspecified. And then later we'll say, well, if rho is constant, then that just becomes minus capital lambda rho. Capital lambda rho s in that case. But I'm not assuming that for now. So 2, 4, 6, 8, time to exponentiate now to undo this. So therefore, I lambda of s is I lambda naught e to the minus that integral, e to minus the integral from 0 to s of capital lambda rho ds prime. Sorry. No, okay, yeah, that's fine. Yeah. I'm happy with it. Okay. If capital lambda is a constant, which that's probably okay, But notice here I'm not assuming that either. Capital lambda could be varying because the composition of the beam could vary. The composition of the gas could vary along the beam. So if capital lambda is constant, if it's the same composition all the way along, and also rho is constant, then that simplifies to I lambda equals I lambda naught e to the minus kappa lambda rho s, because the integral, you pull the kappa lambda rho out, and then the integral just becomes minus s. So, or the integral becomes s. So then you would just get I lambda equals I lambda naught e to the minus kappa lambda rho s, and that's just a straight up decaying exponential. So that makes sense if you think about it, because if you think of radioactive decay, the number remaining is the number you started out with times e to the minus lambda t, where lambda is a decay constant. So you get an exponential decay because the number that decay at any small time interval is proportional to the number of atoms that are still there, and that's exactly what leads to exponential decay. Here, rather than time, it's distance that's involved, because the amount scattered in a little distance is proportional to how many photons are still there. So now distance is playing the role of time, if you will. The number scattered is proportional to the number that's still left. And so then you'll get an exponential decay with distance instead of time in that situation. So just as we can talk about an e-folding distance, or just as we can talk about like the half-life or the e-folding time for radioactive decay, we could talk about a half-life in terms of distance for the photons, and over what distance do half of the photons get taken out of the beam. Easier than that is over what distance does the intensity fall to 1 over e, which is very natural because it's natural logarithms we're talking about. So the E folding distance distance for which I lambda is equal to I lambda naught over E, that's the E folding distance. Is going to be 1 over kappa lambda rho. Because if I plug S equals kappa lambda rho, I get E to the minus 1. For that, it's 1 over kappa lambda rho. And that's also the mean free path for the photons. That's the photon mean free path, which I'll show. I will prove that. So we will show that for this case where you get an exponential decay, that actually is the photon mean free path, because let's let P of S ds be the probability that a photon travels a distance between S and S plus ds before absorption. So in other words, the idea here is I start out here at some point, and I want to know what's the probability that somewhere between, what's the probability that it scatters somewhere between there and there?
Okay.
Right, so here's a bunch of photons. Some photon might get scattered here. Some other photon might get scattered here. What's the probability that any given photon will scatter in this little slice right there? Kind of like with people. What's the probability? Well, people, okay, to be macabre, people die at various ages, and life insurance people are in the business of predicting, the probability that somebody will die between the ages of 61 and 62, for example. So here it's, what's the probability that photon will leave the beam between S and S plus ds? So P of S ds is probability that the photon travels a distance between S and S plus ds before absorption. Or scattering. And again, even though I've said absorption includes both true absorption and scattering, I still think it's better to say absorption slash scattering, to be clear that I really mean either one. It either gets eaten or it gets lured away by its friend. So in other words, what's the chance it will scatter in that little slice? Well, that's the fraction of the population that scatters in there. So in other words, if 1,000 photons are traveling this way and 5 of them scatter in this slice, then each photon had a probability of 5 over 1,000 of scattering in that little slice. So that's the fraction of the original population that scatters in this interval. This is that time of year where if I'm wearing my jacket, I'm too hot, and if I take my jacket off, I'm too cold.
Yeah.
So I can't win. So I guess what I have to do is oscillate.
If you oscillate once you lose them, and then you.
Yeah. And then I'll be back to where, oh, I'm cold, so I put my jacket on again. So I'm truly the harmonic oscillator when it comes
Did you do that? Yeah.
Whereas I like to say the harmonic oscillator. So that will be kappa lambda rho I lambda ds divided by I lambda 0. In other words, kappa lambda rho I lambda ds is the fraction that's scattered in ds. That's how we define things. I left the minus sign off because I just want the amount, not that the change is negative. I don't care about that. I lambda naught is proportional to the original number of photons. So this ratio will be the probability of scattering in that little interval between s and s plus ds. But if we have this exponential decay here, I can plug in I lambda naught e to the minus kappa lambda rho s for I lambda in there. So this becomes kappa lambda rho I lambda naught e to the minus kappa lambda rho s ds divided by I lambda naught. So from this we infer that P of S ds is equal to kappa lambda rho times e to the minus kappa lambda rho s. And then we still have to multiply by the ds, because the I lambda naught is canceled. So then, the mean free path for wavelength lambda photons, well, that will be the average value of S that they reach before scattering. And what that means is to add up for all possible values of S for which they could scatter. They could scatter anywhere from right away at S equals 0. In principle, one could travel out to infinity before scattering, because the beam, in principle, there's no limit, and it's an exponential decay. So it's that deal where mathematically the intensity never goes to 0. Now, in reality, it does, because if you've got a finite number of photons, eventually the last one goes away, just like in a radioactive sample. In principle, mathematically, you always have some sample left, but it's really made of atoms, so eventually the last atom decays. But mathematically, the photons just keep going forever. You can imagine starting with an infinite population, and there's always some left in that case. So we integrate from 0 to infinity, all possible values of S, of S times P of S ds. In other words, this is the principle that the average value of a quantity is what you get when you add up value times probability of that value for all possible values.
I see.
That's in general what an expectation value and average value is. You add up value times probability of getting that value for all possible values. That's another way to find an average. Adding it up for every possible value, which is 0 to infinity. In other words, all the possible values of S go from 0 to infinity. This is what you're doing, for example, I'll remind you from quantum mechanics. The expectation value of X, you go minus infinity to infinity, psi star of X, psi of X, dx. Well, psi star psi is the probability density for finding the electron at x, and then probability density, so in other words, this really is, another way to write it, is it's x times the probability of x dx for all possible values of x. Here the only difference is we don't consider negative s because the beam is starting out at some particular location. So, well, we can actually do this integral because this is integral from 0 to infinity of s times that. Kappa lambda rho e to the minus kappa lambda rho s ds. And then this is an integral we can do by parts. This is the integral from 0 to infinity of s times minus dds of e to the minus kappa lambda rho s ds, because kappa lambda rho e to the minus, sorry, I needed, no, yeah, that's fine. Because if I take dds of e to the minus kappa lambda rho s, that's minus kappa lambda rho e to the minus kappa lambda rho s. So then, if I take minus dds, I get rid of the minus sign. So this derivative is in fact kappa lambda rho e to the minus kappa lambda rho s. So this is another way of writing, you might have seen this before, as you write in the middle of u equals s, dv is blah blah, and then you, okay, but this is another way to write integration by parts. This will be then the integral from 0 to infinity of e to the minus kappa lambda rho s ds, and then we have to add the boundary term, right? Integration by parts, it's like the integral of u dv is uv minus the integral of v du. And so the boundary term is the uv part, where you multiply the two functions together. So this will be minus s e to the minus kappa lambda rho s evaluated between 0 and infinity. That's the boundary term in the integration by parts. And this is the vdu term in the first, the integral there is the integral of vdu. And so if we do this, then what do I want to say? For this piece, what do I get when I plug infinity into e to the minus kappa lambda rho s? If I plug s equals infinity, I get e to the minus infinity, which is 0, and then the lower limit also 0. So this term goes away. The boundary term goes away because it's 0 on both limits.
Won't it be s for?
I'm plugging in s equals infinity and s equals 0, and s is already there in front too.
0.
Right, so in the upper limit it goes away because of the exponential, in the lower limit it goes away because of the s in front.
I see that.
And so then we just need to integrate this, but this function is perfectly simple to integrate, right? So the integral of that, the antiderivative, is e to the minus kappa lambda rho s divided by kappa lambda rho, and then we'll evaluate it at 0 to infinity because it's got a minus sign integral. So I just flip the limits here to account for the minus sign. And so when I plug in 0 for the upper limit, I get e to the 0 over kappa lambda rho. And when I plug in infinity, that the exponential goes to 0. So in other words, what I get is just 1 over kappa lambda rho in the end.
And that's very cool.
And that's what I was trying to show, that the average distance a photon travels before scattering is 1 over kappa lambda rho. The photon mean free path is indeed 1 over kappa lambda rho, which was the claim. So here's where we say QED, which stands, of course, for quite easily done.
Quite
learned that from one of my physics profs when I was an undergrad, Case Western Reserve. It said QED, quite easily done. Okay, that's not what it really stands for, but I like thinking of it.
It is true though, because that's what like whenever people write journals, it's just asking, like even in your doctorate when you said
Oh yeah.
readily calculated.
Yeah, I know. There should be a law against that. But yeah, even I fall prone to that, right? A little calculation shows, right? There should be a law that says you have to say, when I say a little calculation, do I mean half a page? Do I mean 20 pages? Right? It's not fair because it's like, okay, let me see if I can prove this. And then you don't know when you're 5 pages into it, is it 1, I'm stupid, or 2, it's really 20 pages and the damn author didn't say so. Right? You know? So.
That's what I was thinking too. I was like, I think I'm just too dumb.
Right, and then it turns out, no, it's actually that they just were weasels and didn't tell you that it actually took them 20 pages. Yeah. Which is actually kind of bad because there must surely be papers out there, because I can tell you that reviewers don't always check the calculations for exactly that reason. So there must be published results that are BS because the author made an error in their calculations, and the reviewer didn't catch it because the reviewer is like, you know, God, I've only got so many hours in the day. You know?
Yeah, and
so
many papers to review,
right.
So you can't run through it.
So there must be some BS results out there from people making mistakes in their algorithm, or the reviewer might make the same mistake, you know, because even if the reviewer says, can you send me your calculations? Well, it happens all the time. A student says, can you help me with this? I can't get this result. And I go through the calculations, everything looks right because they've been sucked into their math, you know. If you try to check somebody else's math, everything looks reasonable. But if you did it yourself, you wouldn't have divided by 2 and forgotten to cut it in half, you know.
Yeah,
you know, so.
It's hard to spot.
Yes. Right. So we can say that the photon mean free path is 1 over kappa lambda rho, and we'll also say that that's 1 over n sigma lambda, using our result from before, where sigma lambda is the photon absorption cross-section. Which is, again, it's got units of area. It's kind of how big does the atom look to photons? How big of a sphere would absorb, in other words, how big of a sphere that absorbs every photon that touches it would absorb the same number of photons that the actual atoms do, or the actual electrons do. That's what we mean by an absorption cross-section. What size of a hard sphere that absorbs anything that hits it, even really a hard disk, what size would that have to be? What area would it have to absorb the same number of photons that the actual particles do? That's what the absorption cross-section is. Okay? What questions do you have?
So far, so good.
Okay?
I like the variation.
Yeah, I like that too. Yeah. So now we're going to make a new friend called the optical depth. And that's another one we're just keep going back to over and over again. So the optical depth is defined like this. D tau lambda, the change in the optical depth, is equal to, by definition, minus kappa lambda rho ds. In other words, in what we wrote before, we gather up the kappa lambda rho ds part with a minus sign. We gather all that together and we call that the change in the optical depth. So this is our definition, and now we will start to say why we make this definition. So the minus sign, notice here, means that optical depth and distance along the beam and direction of travel change in opposite directions.
As the further away you get,
Yeah. Right. And that's because, ultimately, it's because we're going to think of photons coming towards us from somewhere inside the star, or from some place far away, okay? So if photons are approaching me from over there, I want to say that the direction they're moving is the direction of increasing S. But optical depth is what I'm seeing. So the further away the source is from me, the greater is the optical depth of that source. But the source we'll think of as being typically at S equals 0, and I am at optical depth equals 0. So the increase in opposite directions is the idea. So the minus sign means tau lambda increases in the direction opposite to that of light travel, opposite to that of light travel. Minus sign means tau lambda increases in the direction opposite to that of light travel. As we look back along the ray, so if we wanted to draw a picture, there's the observer's eye. There's the source of light. And so S increases along the beam direction, the light traveling towards you, but tau lambda increases in the other direction, away from you. So you typically are at tau lambda equals 0, and the source you typically say is at S equals 0. And so then, what we'll imagine is, even though there's probably no such thing, that's supposed to be horizontal, so let me draw it. We're going to imagine that we can say that there is a top of the atmosphere. Now, a stellar atmosphere or the Earth's atmosphere actually typically just fades away exponentially. There's no sharp boundary. But eventually the pressure is so low that you might as well say you're above the atmosphere. So it's kind of like the Earth's atmosphere, there's no sharp boundary to where it stops. But by the time you're 100 kilometers up, the pressure and density are so low that that's been somewhat arbitrarily defined as the edge of space. So if, you know, when there's been like contests or whatever, to say that you've launched something into space, the definition is it gets to a height of greater than 100 kilometers. That's just a definition. It's like 62 miles, 100 kilometers. So you can call that the top of the atmosphere, for example, which is really kind of a definition. And so here will be S equals 0. So in other words, I'm going to say I want to look at photons that start out that far below the top of the atmosphere.
And S is going, okay, S is going straight up.
So actually, no, we're not even going to do that. Straight up will be the z-axis.
Oh, okay.
And we're going to say that we're looking at some angle to straight up. In other words, this is where we can come in with like limb darkening.
Ah, I see. Very good.
Uh-huh. So the observer is looking at photons coming at some angle theta to the vertical. So S is increasing along that direction. The top of the atmosphere, we say, has optical depth 0. And that means you do too, because the change in the optical depth is going to be 0 if you're above the atmosphere, because there's nothing left anymore. So in other words, tau lambda is 0 at the top of the atmosphere and everywhere above as well. So we're just making that definition. The optical depth is 0 at the top of the atmosphere and everywhere above, because there's no more absorption after that. And the change in tau lambda depends on kappa lambda and rho, but rho is 0 as long as you're outside the atmosphere. So where the source is, S is 0, but tau lambda is bigger than 0, because remember, tau lambda increases as you go opposite the direction of light travel. The further away the source is, the bigger its optical depth is. So now we start with our definition of tau lambda, and we say from that the change in tau lambda will be the integral from tau lambda to 0 of being a good mathematical citizen, d tau lambda prime. So I integrate along the beam at optical depth tau lambda where the source is, up to the top of the atmosphere where the optical depth is 0, add up the change in tau lambda, and that will be the total change in tau lambda between those points. So that'll be 0 minus tau lambda, because I'm just integrating d tau lambda prime. And then, if I'm integrating on this side, let's integrate on this side as well. So that'll be minus the integral from 0 to s of kappa lambda rho